Hi everybody, I hope this video finds you well. In today's video, we're going to be continuing our discussion of section 7.7, which is about numeric or approximate integration. In today's video, we're going to be focusing not so much on learning new ways of approximating definite integrals, but instead we're going to be interested in developing and understanding some formulas that help us estimate and understand the error that occurs when doing these approximations. Now, in today's video, there are going to be a couple examples that involve doing some calculations via a calculator. So if you have a calculator, you might want to have that easily accessible as you follow along in this video. Now, if you remember from the last video where we introduced a couple numeric approximations, some of which you might have seen from Math 190. Those were the left end and right endpoint approximations. We also discussed the midpoint approximation and introduced a new one called the trapezoidal approximation. We're going to be focusing on developing some formulas that understand and estimate the error that occurs in each of those approximations. So let's go ahead and get started taking a look at what we have right here. So for the purpose of these four formulas, we're going to have one for each of the approximations that we've covered so far. We're going to suppose that we have a function f of x on some interval a to b, right? So that's, of course, going to correspond to the bounds of the definite integral you're working on. Further, we're going to suppose that k1 is an upper bound on the absolute value of the first derivative, and k2 is an upper bound on the absolute value of the second derivative of the function on that interval. So you'll notice the notation that we're using here. K1, the subscriptive 1, corresponds to the first derivative. K2, the subscriptive 2, corresponds to the second derivative. The reason that in these two formulas, or these two sort of suppositions here, that we're mentioning the absolute value of the first and second derivative is just because we want these things to be an always positive value. If we have those upper bounds, then we have the following four error-bound formulas. In our notation here, E sub r is going to be the error for the right endpoint rule. E sub L is going to be the error for the left endpoint rule. E sub T is the error for the trapezoidal rule, and E sub M is the error for the midpoint rule. And in that case, we get these four formulas here. You'll notice, first of all, that the error bound for the right endpoint and the left endpoint rules are the same. It is k1 times b minus a squared over 2n. For the trapezoidal rule, it's k2, remember that's the bound on the second derivative, times b minus a cubed over 12n squared. And for the midpoint rule, it's k2 times b minus a cubed over 24n squared. Now, there should be a couple things we keep in mind here as we understand and look at these error-bound formulas. First of all, you'll notice that as I'm talking about this, we keep saying error-bound formulas. These formulas do not tell us what the error is exactly going to be. They actually tell us the worst case sort of scenario. They tell us the maximum that the error might be. In other words, the actual error, in other words, the difference between the approximate value that we get through whatever method we're using and the actual value of the definite integral, the actual error there will always be less than or equal to what we're getting from these error-bound formulas. And that's why we have that less than or equal to symbol in each of these. The actual error will always be less than or equal to what the error-bound formula says. You'll notice that we have absolute value on each of these. That's because in these error-bound formulas, we're not interested in if we're overestimating or underestimating. We're not worried about whether or not the error is positive, negative. We're just interested in the magnitude of the error. All right, let's talk a little bit about what we're seeing in these formulas. So the first thing you'll notice is that in each of the formulas, the b minus a component appears in the numerator. And that should sort of make sense because the b minus a component is measuring the length of the interval that you are looking at the definite integral on. The larger the interval, right, that means the sort of longer distance that you're trying to estimate the area over, and that's going to make your approximation less accurate. So the larger the interval, the more error there's going to be. That's why it appears in the numerator there. You'll also notice that in the denominator, right, you have this n, which is your number of partitions. So your number of partitions is how many things you divided your interval into, how many approximations you're making. So notice that it makes sense that that n shows up in the denominator, because the more partitions, the more approximations you do, the more accurate you should be. Now, perhaps the most sort of confusing component is why this K1, or in the trapezoidal rule and the midpoint rule, the K2 appears in the numerator. You can sort of think about those as measures of how much change, or how rapidly the function is curving. So if you think about it, in the right endpoint and left endpoint rule, this is saying that it is the derivative, the slope, that dictates, right, how much error there is going to be. Another way to sort of think about that is that the right endpoint and left endpoint rules are only perfect approximations when that K1 is 0. Now, if you think about that, that's saying that they're only perfect approximations when that first derivative is always 0. Now, the first derivative being always 0 means that you're talking about a straight horizontal line. And that should sort of make sense, right? So if you want to sort of diagram that out, the only way the left endpoint and right endpoint approximations are totally accurate is if you have some sort of function that over the interval you're working on doesn't change at all. In other words, it's a straight horizontal line. It's something where the first derivative is 0. Now for these guys, the midpoint rule and the trapezoidal rule, you'll notice that it's based on K2. K2 is not a measure of the slope. It's really a measure of how much concavity there is. Said another way, you can say that the trapezoidal rule and the midpoint rule are only really perfect approximations when K2 is 0, when the second derivative is 0. Now, functions that have a 0 second derivative, those are functions that have no concavity. Those are functions that have a constant slope. Those are just straight lines. So that means those approximations, midpoint rule and trapezoidal rule, are perfect approximations when you're working on something that is a straight line. Now, obviously, that's very clear if you think about the shape you're sort of drawing there. I mean, that is a trapezoid, but it also makes sense the way the midpoint rule works, because if you imagine that midpoint there, and then you're drawing off to those two sides, yes, you have a little bit of a sort of overestimate, but that is balanced by that underestimate, so it's a perfect approximation there. So that right there, in this class, we don't quite have the mechanisms to prove that these are the error-bound results, but I hope that that sort of quick discussion sort of justifies why they make sense. And again, remember, it basically is saying that if your interval is larger, then there's going to be more error. If you do more approximations, more partitions, it's going to have a smaller error. And for the right endpoint and left endpoint, it's based on how much of the first derivative there is, how much of a slope or rate of change there is. Whereas for the trapezoidal rule and the midpoint rule, it's based on how much concavity there is. Now, we're going to go ahead and take a look at an example in just a moment. But one thing I want to mention is that when we're doing this computationally, keep in mind that K1 and K2 are upper bounds, meaning we're going to have to determine the first or the second derivative, consider it an absolute value, and then attempt to maximize it on the interval. So we'll take a look at that as we get started into our examples. So let's go ahead and take a look at our first example that'll hopefully give you a better sense of what these error-bound formulas are saying and how they relate to the approximations that you guys learned about in the previous video. So for our first example, we'll zoom in just a little bit there, we're going to consider the definite integral from 1 to 5 of 1 over x dx. Now, this is definitely, if you'll pardon the pun, this is definitely an integral that we know how to do through our knowledge of antiderivatives and the fundamental theorem of calculus. We're using such a simple example to start off with because we are actually going to go ahead and do this from an approximate standpoint, then an actual direct computational standpoint, and then we're going to actually use that to know what the errors are and show that those errors fall within the error bounds. So let's go ahead and talk about each piece here. The first thing we're going to do in part A is we're going to determine the error bounds for the left endpoint rule, the trapezoidal rule, and the midpoint rule with 4 partitions. So we're going to go ahead and use the formulas from the previous page to go ahead and do this. So to start off with, let's look at part A, and let's start off with that left endpoint rule. So if we go back over, we can see that the left endpoint rule, right, uses this guy right here. So we'll just carry that over and we'll start with that formula. So we know that the maximum error, that E sub L, an absolute value, is going to be less than or equal to K B minus A squared over 2n. And again, we're just grabbing that directly from here. If we were doing the right endpoint approximation, we would use the same formula there. So we've got our expression right there. Now, to plug into this formula, sorry, that's a K1 there, we basically need to know 4 things. We need to know K1, we need to know B, we need to know A, and we need to know N. So let's start with the sort of easy ones, right? B and A, they represent the ends of the interval. That's that 5 and that 1. So we know that that's going to be 5, that's going to be 1. And of course, we're doing this with 4 partitions, so we have N equals 4. To find that K1, though, we're going to go ahead and have to determine the first derivative. So let's go ahead and remind ourselves this right here. This is going to be a upper bound on the absolute value of the first derivative. So let's go ahead and find that first derivative. Our function that we're trying to integrate here is 1 over x, which of course is just x to the minus 1. We go ahead and take that first derivative, and we'll get negative x to the minus 2, or if you prefer, negative 1 over x squared. Now, if we look at that, of course, if we put that in absolute value, the absolute value of this is going to be 1 over x squared on the interval 1 to 5. Now, our question is we need to find an upper bound for this, right? In other words, where is this first derivative largest on the interval 1 to 5? Well, for some functions, right, you could do this like a Math 190 problem, a maximization problem. You could take another derivative, find the critical values, and then test the 2 endpoints and the critical values to see which one gives you the largest overall value. But in this situation, and in a lot of the situations you're going to be asked to do, there's a much simpler way to do it. You can recognize that this function, 1 over x squared, is a monotonic function. Monotonic just means it's either strictly increasing or strictly decreasing. Since the x squared appears in the denominator and the numerator is always constant, this function is strictly decreasing. The larger x values you put in, the smaller outputs you get out. So that means if we're looking for an upper bound, if we're looking for where it's maximized, we would want to use the low end of our interval. So let's write that out, right? Strictly decreasing, right? This implies max occurs at the low end, at x equals 1. So let's plug in x equals 1. That means our k sub 1 is going to be the absolute value of the first derivative at 1, which if we plug in 1, of course, is just going to give us 1. So now we know that k1 should be 1. We have everything that's necessary, so let's go ahead and plug that in. That means our error bound for the left endpoint approximation is going to be 1 times 5 minus 1 squared over 2 times 4. And if we go ahead and calculate that, this is just a calculator moment. Don't need to do this by hand or anything like that. It looks like you're going to get 4 squared in the numerator divided by 8, and you're going to get a maximum error of 2. So this is saying that when we do the left endpoint approximation, it is off by at most 2. Could it be off by less than 2? Absolutely. But it will not be off by more than 2. Now, as we'll see in a few moments, when we actually calculate this integral, I believe the actual definite integral is less than 2 overall. So this is a tremendously high potential error. But remember, this is only saying that this is a potential error. Our actual error might be much less than this. All right, let's go ahead and repeat this now for the trapezoidal rule. And we should be able to go through that a little bit more quickly now that we have a sense of the idea. For the trapezoidal rule, we will go ahead and use the trapezoidal rule error bound formula. So that's back over here. We're looking for the trapezoidal one. So it's that guy, k2 b minus a cubed over 12n squared. So we're going to use k2 b minus a cubed over 12n squared. Now, this one is going to require us to determine k2, so we're going to have to do a little work to do that. We'll need to know b and a and n. Now, of course, b, a, and n, they all stay the same, so that's 5, 1, and 4. For k2, unfortunately, we can't just use the value of k1 because this is going to be an upper bound on the second derivative. So this is going to be an upper bound on the absolute value of the second derivative. Well, the good news is, right, that looks a little weird of an absolute value bar there, so let's fix that. The good news is we already have the first derivative, right? So we already have that our function is 1 over x, and we already determined that the first derivative was negative x to the minus 2. Getting the second derivative, one more use of power rule, looks like it would be 2x to the minus 3, or if you prefer, 2 over x cubed. This time the absolute value isn't really doing anything because this function is already always positive on 1 to 5. So we're on 2 over x cubed on 1 to 5. This guy is once again strictly decreasing, right? Because we have that x cubed in the denominator and the numerator is a constant. So as we plug in larger inputs of x, we get out smaller outputs. We're trying to maximize. So this would tell us the max occurs at x equals 1. We plug that into the second derivative, and we get absolute value, second derivative at 1. Plug that in, clearly we just get out 2. So we'll plug in 2, and we should be good to go. This tells us that the maximum error when doing the trapezoidal rule is going to be 2 times 5 minus 1 cubed over 12 times 4 squared. Once again, this is just a calculator exercise, so you don't want to do this by hand or anything. It's going to be 2 times 4 cubed up top, and then divided by 12 times 16. And this comes out as approximately 0.667. So the maximum error with the trapezoidal rule is 0.667. Now, a lot of times people see that and they say, oh, that must mean that the trapezoidal rule is going to be more accurate. Well, that is generally the case with the trapezoidal rule. The error-bound formula can't tell us that because, again, the error-bound formula is only telling us what the maximum error might be. We know that the trapezoidal rule as maximum won't be as bad as the left endpoint, but we don't know what the actual error will be. These formulas are only telling us worst-case scenario. All right, let's go ahead and do one last one. We wanted to finish up this by looking at the midpoint rule. So we can go back over midpoint rule right here. Basically very similar to the trapezoidal rule, except we have a 24n squared in the denominator. So let's go ahead and do that. So for the midpoint rule, it's going to be less than or equal to k2 b minus a cubed over 24n squared. The k2, b, and a, and n here. Now, of course, the b is 5, the a is 1, and the n is 4. Now, k2, this references the same k2 on the same function on the same interval, so we know we are safe in just reusing the value of 2. Now, if we shifted intervals, if we said, let's look at the definite integral from 6 to 10, well, then that k2 would change. If we looked at a different function, obviously that k2 would change. But in this case, we've already done it for this function on this interval, so we can just go ahead and directly carry it over. So if we go ahead and evaluate that, we have the maximum error for the midpoint rule is 2 times 5 minus 1 cubed over 24 times 4 squared. And if we go ahead and evaluate that, well, that's going to be 2 times that 4 cubed, and then divided by 24 times that 16. And that should come out as 0.333. Now, of course, we could have just sort of known this right off the bat, because since the only difference between this error bound formula for the trapezoidal rule, and for the midpoint is a change from 12 to 24. So of course the maximum error for midpoint is always half of the maximum error for the trapezoidal rule, right? So we could have just said, let's just take half of this and been done with it, but I think it's worth seeing the formula in action this whole time. So in summary here, if we just sort of zoom out a little bit, we basically know that the worst case scenario for 4 partitions with the left endpoint rule is an error of 2. Worst case scenario for the trapezoidal rule with 4 partitions is an error of 0.667. And worst case scenario for the midpoint rule with 4 partitions is 0.333. Now we're going to basically finish this up by actually seeing what the error is and confirming that the actual error is always less than this maximum error. So let's go ahead and do that. Let's go ahead and give ourselves an extra page, zoom in a little bit, and we'll go ahead and move on to B here. Now for B, we're going to go ahead and write down the expressions for and evaluate L4, T4, and M4. Now this is going to be very similar to what we did in the previous video. So let's go ahead and write this out. We have our integral from 1 to 5, 1 over x dx. We're doing this you can think about the sort of number line here. We're going from 1 to 5, right? Our delta x is b minus a over n. In this case, our delta x is 5 minus 1 over 4. So our delta x is, of course, 1. That means the pieces we're using, if we go by ones, are 2, 3, 4. So that means as we go to do our approximations, if we use some colors here, we're going to do our left end point approximation. That means we're going to use this guy, this, and this. Then when we go ahead and use, for our second one, we're going to do the trapezoidal rule. Remember, for the trapezoidal rule, you will go ahead and use all of these. Though, remember that when you do the trapezoidal rule, these middle ones get weighted twice. They're basically the left end. This guy would be like the left end of this first trapezoidal, and then he'll be the right end of the second trapezoid. So they'll be used, these middle ones will be used twice, whereas these guys will only be used once. And then finally, for the midpoint rule, we'll have to give ourselves maybe one more color for that. Midpoint rule is going to use in between, which you can find by averaging, right, the ends of those intervals. So that, of course, is going to be 3 halves, 5 halves, 7 halves, and 9 halves. So let's go ahead and write those out. Let's start with the left endpoint approximation. L4 is going to be our delta x, which is our 1, and then times our f of 1 plus f of 2 plus f of 3 plus f of 4. And that, of course, is going to be with f of x equals 1 over x. Now, of course, if we just wanted to set it up but not evaluate it, this would be sufficient. But since this one we actually were asked to evaluate it and we want to compare the actual value of the definite integral against the approximate value, we do want to go ahead and evaluate this. So this will just be some calculator work, right? So if we go ahead and plug this in, we'll get f of 1, which is going to be 1 plus a half plus 1/3 and then plus 1/4. So if we do that, looks like we should get, sorry, we'll make this an approximate value here. This looks like it should come out as about 2.083. So there's our left end approximation. Perfect. Now let's go ahead and do the trapezoidal rule. So the trapezoidal rule, T4, remember this is going to be delta x over 2. And then we're going to have f of 1 plus 2f of 2 plus 2f of 3 plus 2f of 4 plus f of 5. And again, that's with f of x being the function 1 over x. Again, normally we could just leave it like that, but we do want to go ahead and evaluate this. So if we do that, we're going to have 0.5, or that 1/2, times 1 plus 2 times 1/2 plus 2 times 1/3 plus 2 times 1/4 plus a 1/5 at the end. And if we go ahead and evaluate that, we get about 1.683. So, different approximation for sure. Notice it's not a surprise that the trapezoidal rule is lower here. This function, 1 over x, if you think about what it sort of looks like, it's a rational function like that. So the left endpoint approximation when you're doing that is doing things that look like this, which are going to be overestimates. So it makes sense that this came out with sort of a high approximation and this one was a bit lower. Let's go ahead and get the midpoint rule. So M4 here. M4 uses delta x, so it's just going to be 1 and then times f of 3 halves plus f of 5 halves plus f of 7 halves plus f of 9 halves. And again, that's with the function f of x equals 1 over x. Remember all of this, right? The reason we're just mentioning this is because it's a good reminder that you don't need to know the antiderivative for the function. That's the whole point here, right? We can do this just knowing the function itself. We do know an antiderivative for 1 over x, but we don't need to do these approximate integrations. Let's go ahead and get this value here. So that M4 is going to come out as approximately. That is going to be 2/3 plus 2/5 plus 2/7 plus 2/9. And then that is going to come out as about 1.575. So there we go. There's our 3 approximations. Let's go ahead now and continue on by actually directly evaluating this integral. Now this is really only for the purpose of actually comparing the actual error versus the error bound. Remember, normally the reason we do numeric integration is because we don't want to actually have to directly evaluate it. But for the purposes of this exercise, we picked one where we would know how to directly evaluate it. So let's go ahead and do that. So for part C here, we're actually going to evaluate the integral from 1 to 5 of 1 over x dx. Remember, we do that by determining its antiderivative, which is ln absolute value x, and we will be doing that from 1 to 5. That's your fundamental theorem of calculus there. Plug that in, we get ln absolute value 5 minus ln absolute value 1. Of course, the absolute values don't matter here. This just is ln 5 because ln of 1 is 0. And if we go ahead and just determine that, so we have a decimal, this comes out as approximately 1.609. Now, as you can sort of see, this 1.609 is pretty close to what T4 and M4 were saying. It's not identical, of course, and we only did this with 4 partitions. So, I mean, this was a very, very sort of rough approximation. The L4 is pretty far off. It's not a great approximation, but again, left endpoint and right endpoint are not expected to be particularly great approximations, especially with monotonic functions where they're always overestimating or always underestimating. But let's go ahead and actually check the actual errors versus the error bound. So let's actually go ahead and calculate. So we'll go ahead and get E sub L, right? So E sub L, if we're just interested in the magnitude, would be the absolute value of what we actually had as our integral, 1.609, minus the predicted value, 2.083. We're just doing it in absolute value because that's what we're sort of interested in. So we're saying this is what the actual value of the integral was. This is what the left endpoint approximation predicted. And if we go ahead and do that, we will see that that error in magnitude, sorry about that, in magnitude is about 0.474. And if we look back, we said over here that the worst case scenario would be 2. And of course, 0.474 is less than or equal to 2. Now, I'm putting a little check mark there to confirm that that's true, right? But of course, the whole point of those error-bound formulas is that it guarantees that this actual error will be less than that error-bound every time, right? That's not something we need to check or we need to confirm. This is just to demonstrate the meaning of the error-bound formula here. All right, let's do the same with E sub t. E sub t would be the actual value of the integral, 1.609, minus the prediction, which was 1.683. And again, we're just doing that in absolute value. So let's go ahead and get that. That's going to be 0.074. Notice that that's a much better approximation, much lower error. And if we check, that was supposed to come in as less than 0.667, which it certainly did. So that is less than 0.667. Give ourselves a check mark. Very nice. Last one, the actual error for the midpoint rule was 1.609, the value of the definite integral, minus the prediction, 1.575. That, if we do it, 1.609 minus 1.575, that came out as 0.034. And if we go back over here, it was supposed to make sure that it came in less than 0.3333, which it absolutely did. So that guy also made it in there. So this shows you with this first example that those error-bound formulas really do provide you the maximum error that might occur. Notice that in this case, right, all of the errors, of course, came in less than those error-bound formulas. The midpoint rule turned out to be the best approximation. That is not always the case. The midpoint rule is often a better approximation than the trapezoidal rule or the left endpoint rule. But again, we don't know that based on the error-bound formulas. We know that based on these computations that we did actually finding the actual error here. Now, before we get to our next example, you might be asking yourself, what is the purpose of these error-bound formulas? Because while this example here hopefully was sort of interesting and illustrative of what the error-bound formulas are saying, we wouldn't really use it on a situation like this because, again, the whole reason we were able to get the actual integral was because we knew the antiderivative, and if we knew how to do the antiderivative, why would we bother with a numeric method? Well, as you guys will see in the next example, the main use of the error-bound formulas is not to determine the maximum error, but it's actually to determine the number of approximations you need to establish that your error will be less than a certain threshold. In other words, if you look back at the formulas, what we'll be sort of doing is we'll be saying, if this is the error bound, let's make sure that this error comes in, say, less than 0.1 or 0.01, some maximum amount of error. And we'll set this equation up to say this less than, say, 0.01. And then once we do that, we'll be able to solve for the number of partitions necessary to make sure we have that level of error or less, right? Basically treating that error like a threshold. So let's see how to do that with our next example. So we'll go ahead and move over to here, and we'll consider this definite integral. So we're going to be looking at the definite integral from 0 to 1 of e to the x squared dx. Now, I believe we've talked about e to the x squared in some other situations. E to the x squared is a very sort of typical example of a function, simple function, right? It's just the x squared function being composed into the exponential. It's a very simple function, but it does not have a closed form antiderivative. And when we say that, we don't mean like we haven't learned a closed form antiderivative for it. It means there literally does not exist a closed form antiderivative for e to the x squared. So mathematicians have proved that there is no closed form, meaning a function written out with other elementary functions that acts as the antiderivative of e to the x squared. So there is no way to directly integrate this and plug in the bounds. We have to use approximate integrations like the right endpoint rule, like the trapezoidal rule, like the midpoint rule to approximate this integral. What we're going to do though in this problem is we're going to say maybe our threshold is 0.01. We don't want to have more error than 0.01. So how many partitions, how many approximations would we need to do to make sure we have error less than 0.01? So let's see how to do that. In part A, we're going to be working with the right endpoint rule. So if we go back, we can grab the right endpoint rule formula, right? Remember, it's the same as the left endpoint rule formula. It's that k1 b minus a squared over 2n. So let's set that up. Let's remind ourselves that the error from the right endpoint rule is going to be less than or equal to k1 b minus a squared over 2n. Now, this is saying that the actual error is going to be less than this. And we want the error to be within 0.01. So we want to make sure that our error is less than 0.01. So let's make this less than 0.01. And we're going to focus on this portion here, making sure that this error bound is less than 0.01. So let's rewrite that so we don't have like a weird double inequality. We're going to have b minus a squared over 2n less than 0.01. Now let's make a little table of the stuff we know, k1, b, a, and n. Now keep in mind, b and a should be easy, right? These are the ends of the interval. They're just the bounds of the integral there. So that's 1 and that's 0. N, of course, is the number of partitions. This is what we're looking for. So this is our end goal. And k1, well, we learned that that's an upper bound on the first derivative. So let's go ahead and find that. So we can take that over here. So k1 is going to be, let's just scoot that down a little bit, upper bound on the first derivative there, on the absolute value of the first derivative. So our function is e to the x squared. While e to the x squared, we don't have an antiderivative for it, we do certainly know how to differentiate it, right? It's just chain rule. The derivative of that e to the x squared is e to the x squared and then times the derivative of the inside, which is 2x, or rewritten, it's 2x e to the x squared. Obviously, the absolute value here, right, doesn't do anything, so absolute value of the first derivative is just 2x e to the x squared. Now, once again, we could try to say, okay, maybe let's take another derivative of this, find critical values, plug in the critical values, plug in the ends of the interval, but it should be very clear that as x gets larger, 2x gets larger, and e to the x squared gets larger. So this function is also monotonic, but it's strictly increasing. Now, if it's strictly increasing, right, that means as we put in bigger inputs, we get out bigger outputs. So our maximum should occur at the furthest value of our interval. So that means, right, we should choose x equals 1, right, the largest value of x on our interval. That means k1 here is going to be the absolute value of the first derivative at 1, which if we plug in is just going to be 2e. Now, of course, in a moment, we'll use our calculator to actually evaluate that when we plug it in. But for now, let's just carry that as a 2e. So there we go. We have our k1. Now we can plug this stuff in. So if we do that over here, we have 2e times 1 minus 0 squared over 2n less than 0.01. And if we do a little manipulation, right, we can bring this n over here and the 0.01 down. Notice that this just becomes 2e, that 1 minus 0 squared is just 1, then times 2 times 0.01 less than n. Now let's go ahead and evaluate on our calculator that left side. So that's going to be 2 times that e, and then divided by 2, and then divided by 0.01. So this is going to come out as about 271.8 or so, has to be less than n. Now notice that this reads correctly. This is saying that n, the number of partitions, must be greater than 271.8. Now the number of partitions is the number of rectangles, right, that you're using, so it has to be a whole number. So we can say that this is at least 272 partitions. That's saying that if you did at least 272 partitions, so 272, 300, 500, whatever, but at least 272, the error you would get would be no more than 0.01. Could it be a lot less than 0.01? Absolutely. But it won't be any more than 0.01. That is guaranteed. That's what this is saying. So perfect, right? Now we know how many partitions we would need to do to make sure that we're within 0.01 of the true value. Notice just a quick thing about sort of the rounding in this moment of going from this sort of decimal to this whole number here. Even if you were just doing rounding, all of us would sort of say 271.8 is going to become 272 because the 0.8, right, is 5 or higher, so we know to round up. But keep in mind this is an inequality. So even if it said something like 271.1 is less than n, well, that's saying 271.1 is less than n. So n has to be bigger than that. N has to be a whole number that's bigger than that. So we would still choose 272. So we're always rounding up because we have to choose the next largest whole number. All right, let's go ahead and try this for b with the trapezoidal rule. So with the trapezoidal rule, we want to go back and make sure that we grab our formula for the trapezoidal rule. It's going to be this guy right here, that k2 b minus a cubed over 12n squared. So let's go ahead and write that out. Same way that we did beforehand. We want the actual error from the trapezoidal rule. We know that that's going to be less than k2 times b minus a cubed over 12n squared. And then we want that to be less than 0.01. So if we rewrite that, we're really working on k2 b minus a cubed over 12n squared must be less than 0.01. If we go ahead and make a table of what we need here, we are looking for k2, b, a, and n. Of course, b and a are still 1 and 0, and n is still what we're looking for. Now, unfortunately, k2 we're going to have to calculate because, well, k1 is based on the first derivative, k2 is based on the absolute value of the second derivative. So let's go ahead and do that here. So back up here, we know if we sort of mimic our same approach, k2 is an upper bound on the absolute value of the second derivative. We know that the function is e to the x squared. We just determined that the first derivative is 2x e to the x squared. And if we do the second derivative, well, unfortunately, this does require a product rule. If we take the derivative of this piece, we get a 2. So we get 2 e to the x squared. And then the other one is 2x. And then when we differentiate the e to the x squared, we again have to use chain rule. We get another factor of 2x there. And if we go ahead and we sort of put all that stuff together, that's 2 e to the x squared plus, what is that, 4x squared e to the x squared. So a little bit messier for the second derivative here, but we got it. Now again, the absolute value doesn't do anything because all this stuff is already positive. So the function we're looking at is this guy. Now if we take a look at this, all of this stuff gets bigger as x gets bigger. So this is strictly increasing. So we're going to choose the upper end of our interval, choose x equals 1. Remember, if it was strictly decreasing, like it was in our first example, we'd go back and choose the low end of the interval. But in this case, we're going to choose x equals 1. So k2 is the absolute value of the second derivative evaluated at 1. And if we plug that in, that looks like we're going to get 2e plus 4e, which I think comes out as 6e there. So our k2 value is 6e. Plugging that stuff in, we get 6e, 1 minus 0 cubed over 12n squared has to be less than 0.01. Again, we're going to do a little manipulation. We're going to bring the n squared over here and the 0.01 back. So this looks like we should get 6e over 12 times 0.01 is less than n squared. And if we square root, we're going to get 6e over 12 times 0.01 is less than n. Now, if we actually evaluate that, so let's go ahead and do that. 6, this is, of course, just calculator stuff. So if we do that, 6 times that e, and then divided by 12, and then divided by that 0.01, and then if we take the square root of that, looks like this should come out as about 11 point, I think we just kept one decimal on the other one, so let's just do the same here. 11.7 is less than n. And then notice that we have to go up to the next whole number, so we would say at least 12 partitions. Now notice that that's pretty crazy, right? If you look at the comparison here, we need to do 272 approximations to get within 0.01 where we're using the left endpoint. Yet if we do 12 approximations, and 12, while it might be tedious to do by hand, would be like certainly well within what you could just do by hand or even more easily with just like a calculator, and you'll be within 0.01 of the real value. So that shows the power of these approximate methods. All right, we have one last part to do here. We wanted to go ahead and do this for the midpoint rule. We'll be able to reuse a lot of our stuff though. So let's go ahead and give ourselves one more sheet. All right, we'll go ahead, mark this as part C. We're gonna take our midpoint error bound. This guy, if we go all the way back, right, it's our last sort of formula that we learned here. K2b minus a cubed over 24. And that does say n squared. Yep, just making sure. There we go. So let's go ahead. That's going to be less than or equal to K2 b minus a cubed over 24 n squared. And then we want that to be less than 0.01. Again, we'll sort of rewrite and just focus on the part of the inequality that we care about, which is this right here. And we want that to be less than 0.01. Now we need to know K2, B, A, and N. Of course, B and A are unchanged, 1 and 0. N is what we're looking for. And this time, because this K2 references the absolute value of the second derivative on the same interval for the same function, we can go ahead and just reuse what we found here, which was that 6e. So let's go ahead and reuse that. So same thing. Plug that stuff in. 6e 1 minus 0 cubed over 24 n squared less than 0.01. Once again, same thing. Let's go ahead and bring the n squared over, the 0.01 back. So this becomes 6e over 24 times 0.01. And that is going to be less than n squared. And then we'll square root that. Square root 6e over 24.01 less than n. Notice that this implies, once we actually go ahead and do the computation, this is 6 times, let's see, that's e, and then divided by 24 times that 0.01. And if we do that, that should come out as about 8.2 less than n. And again, notice that this is a good example, right? Even though we would say we round 8.2 to 8, we're looking for the next whole number that is greater than that. So we would say at least 9 partitions. So you would need to do at least 9 estimates to go ahead and make sure that this thing is going to have an error of less than 0.01. Now, interestingly enough, sometimes people see this and, they sort of say, well, I thought like in the formula, if we look back, that the error bound, the only difference between these two is that this is 12 and this is 24. So shouldn't we just need half as many partitions? Well, actually, because of the fact that this is an n squared, the difference in number of partitions, like if you wanted to try to jump ahead from this answer here to this one here, is not by a factor of 2. It's actually by a factor of square root of 2 because of the presence of that square. Now, you could just jump ahead to this answer by doing that, but considering that the process is already pretty simple just to go ahead and plug everything in, I would strongly recommend just going ahead and plugging into the midpoint formula and working back through it again, just to make sure there's no sort of computational mistake there. So, by the end of this video, what we've really seen is the main use of these error-bound formulas. The main use is to give us an estimate ahead of time, to tell us ahead of time how many partitions, how many approximations we're going to need to do to make sure that our error is below some sort of threshold level. Then, of course, in practice and application, once you knew this, you would run your approximation with however many partitions this told you, and then you would know that your final answer is within at least, right, that error that you've set as your threshold. So this wraps up sort of the second major component of this section 7.7, this numeric or approximate integration. In our next video, which will be the last one about 7.7, we will introduce one final approximation method called Simpson's rule and also discuss an error-bound formula for that approximation as well.